6 minutes. That's all the time astronomers had to coordinate a global emergency response when Atlas appeared in our telescopes, behaving like nothing we'd ever seen before. Picture this: ground control rooms erupting into organized chaos, ESA servers calculating trajectories at breakneck speed, and the most expensive space telescope ever built pivoting away from years of scheduled observations to focus on a single, terrifying anomaly. What they discovered in those crucial minutes of observation has left the scientific community scrambling for explanation, and what we're about to reveal will show you exactly why this discovery is being called worse than anyone expected. On August 6, 2025, the James Webb Space Telescope entered a rare and critical emergency override to capture data on 3I Atlas, an interstellar object unlike anything astronomers had observed before. Normally, JWST operates on a strict schedule, with every observation carefully planned weeks or even months in advance, balancing the delicate choreography of orbital mechanics, fuel consumption, and instrument availability. Pausing this finely tuned program is not done lightly, as even a small miscalculation can cost days or weeks of science, or risk damaging sensitive subsystems. The urgency arose from ground-based observations showing that 3I Atlas was accelerating and displaying unexpected spectral signatures. Within minutes, the mission operations team had to decide whether to override the main science program. Approval for such an override required unanimous agreement from the highest levels of the project, including the project scientist, because the risks were high and the opportunity fleeting. The telescope pivoted, instruments active. 6 minutes. That's all the time astronomers had to coordinate a global emergency response when Atlas appeared in our telescopes, behaving like nothing we'd ever seen before. Picture this: ground control rooms erupting into organized chaos, ESA servers calculating trajectories at breakneck speed, and the most expensive space telescope ever built pivoting away from years of scheduled observations to focus on a single, terrifying anomaly. What they discovered in those crucial minutes of observation has left the scientific community scrambling for explanation, and what we're about to reveal will show you exactly why this discovery is being called worse than anyone expected. On August 6, 2025, the James Webb Space Telescope entered a rare and critical emergency override to capture data on 3I Atlas, an interstellar object unlike anything astronomers had observed before. Normally, JWST operates on a strict schedule, with every observation carefully planned weeks or even months in advance, balancing the delicate choreography of orbital mechanics, fuel consumption, and instrument availability. Pausing this finely tuned program is not done lightly, as even a small miscalculation can cost days or weeks of science, or risk damaging sensitive subsystems. The urgency arose from ground-based observations showing that 3I Atlas was accelerating and displaying unexpected spectral signatures. Within minutes, the mission operations team had to decide whether to override the main science. 6 minutes. That's all the time astronomers had to coordinate a global emergency response when Atlas appeared in our telescopes, behaving like nothing we'd ever seen before. Picture this: ground control rooms erupting into organized chaos, ESA servers calculating trajectories at breakneck speed, and the most expensive space telescope ever built pivoting away from years of scheduled observations to focus on a single, terrifying anomaly. What they discovered in those crucial minutes of observation has left the scientific community scrambling for explanation, and what we're about to reveal will show you exactly why this discovery is being called worse than anyone expected. On August 6, 2025, the James Webb Space Telescope entered a rare and critical emergency override to capture data on 3I Atlas, an interstellar object unlike anything astronomers had observed before. Normally, JWST operates on a strict schedule, with every observation carefully planned weeks or even months in advance, balancing the delicate choreography of orbital mechanics, fuel consumption, and instrument availability. Pausing this finely tuned program is not done lightly, as even a small miscalculation can cost days or weeks of science, or risk damaging sensitive subsystems. The urgency arose from ground-based observations showing that 3I Atlas was accelerating and displaying unexpected spectral signatures. Within minutes, the mission operations team had to decide whether to override the main science program. Approval for such an override required unanimous agreement from the highest levels of the project, including the project scientist, because the risks were high and the opportunity fleeting. The telescope pivoted, instruments activated, and the entire operations center was on high alert, monitoring every telemetry signal as the team raced to ensure nothing went wrong. This emergency intervention was historic because JWST had only performed a handful of overrides since its launch, and none had ever targeted an interstellar object. Every other observation, from distant galaxies to exoplanet atmospheres, was temporarily suspended. The situation underscored the extraordinary nature of 3I Atlas, which was behaving in ways that broke the normal rules for comets, prompting astronomers to mobilize their resources instantly to capture a fleeting window of unprecedented data. The override not only demonstrated the telescope's flexibility but also highlighted the stakes involved in studying interstellar visitors. Unlike typical comets, whose paths and chemical compositions are relatively predictable, 3I Atlas demanded immediate, full-scale attention. Its arrival was a rare cosmic event, and missing it could mean losing the chance to understand a body formed in conditions potentially very different from anything in our solar system. The tension in the control room was palpable as scientists worked against the clock, knowing that any delay or error could compromise the mission, but also that the data they were about to capture could reshape everything we know about interstellar objects. This moment marked the beginning of a high-stakes observation campaign that would uncover chemical, physical, and dynamic properties of 3I Atlas that had never before been recorded, setting the stage for a story of cosmic anomalies, scientific debate, and mysteries that reach back into the very history of human observation of the heavens. Astronomers had anticipated that 3I Atlas would behave like a typical icy comet, slowly releasing water vapor and forming a faint, predictable tail as it approached the sun. Instead, the first data packets from JWST painted a picture that defied every expectation. The comet's coma was saturated with carbon dioxide at levels never recorded before, and the instruments detected metallic nickel in abundance while iron, normally found alongside nickel in comets and meteorites, was almost completely absent. This chemical imbalance was so extreme that seasoned experts in interstellar bodies described the numbers as alarming, even terrifying. The comet was already active far from the Sun, at a distance beyond Jupiter where sunlight is weak and most comets remain dormant. Instead of the usual sublimation of water ice that drives comet activity, 3I Atlas was venting sheets of carbon dioxide gas, a process that normally requires much more heat. The tail, thin and ghostly due to the scarcity of dust, extended for hundreds of thousands of kilometers, growing far faster than standard models would predict. Observations from other telescopes, including Gemini South and Hubble, confirmed these unexpected phenomena, ruling out calibration errors or instrumental glitches. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. Every team cross-checked the data against known comet behaviors and previous interstellar visitors. Even Borisov, the last interstellar object to pass through the solar system, did not approach these levels of carbon dioxide dominance or the extreme nickel-to-iron ratio. The production rates calculated from the spectra showed carbon dioxide pouring out at 8 times the rate of water, a ratio completely off the charts. Dust, normally a major contributor to the brightness and structure of a comet's tail, was nearly absent, making the comet appear almost ethereal, as though it were glowing from the gas itself. Scientists immediately realized that this object was not just unusual, it was a chemical enigma. The composition suggested a parent body formed under conditions vastly different from those in our solar system, perhaps in an environment where water was scarce and carbon dioxide ices dominated. Alternatively, it might reflect an unknown chemical or physical process that had never been observed. Whatever the explanation, 3I Atlas was rewriting the rulebook for how comets form and behave, challenging decades of expectations and sparking intense excitement and concern among astronomers around the world. The implications of these initial observations went beyond mere curiosity. The chemical signatures hinted at a history and origin completely alien to the solar system, raising fundamental questions about interstellar chemistry and the diversity of planetary systems. Scientists were suddenly looking at a visitor whose very makeup seemed to defy the laws and patterns established by centuries of comet studies, signaling that the story of 3I Atlas was only beginning to unfold. Ground-based telescopes immediately began sending real-time observations of 3I Atlas as soon as its unusual behavior was noticed. Every new measurement mattered, as the comet was accelerating unpredictably and its trajectory was shifting by the hour. Teams across multiple observatories scrambled to track its path, gathering positional data that could determine exactly where JWST needed to point. This was not a routine calculation. The object's erratic movements meant even minor delays could result in missing the observation window entirely. ESA servers took the incoming data and ran rapid, complex calculations to produce precise coordinates for JWST. The process required accounting for the telescope's orbital mechanics, fuel constraints, and instrument alignment, ensuring that NIR spec and other sensitive instruments could lock onto the object immediately. Any error, even by a fraction of a degree, risked losing the opportunity to collect critical spectral data or wasting precious observation time. In less than 6 minutes from the initial alert, the emergency override command sequence was transmitted to JWST. The telescope pivoted in real time, its sensors activating as engineers monitored the telemetry for any sign of malfunction. Every eye in the operations room was fixed on the incoming data stream, waiting for the first packets to confirm that the comet was within range and that the instruments were functioning as intended. This coordination showcased the remarkable precision and flexibility of modern space observatories. What normally takes weeks of planning and committee approval was executed in mere minutes, driven by urgency and the extraordinary nature of 3I Atlas. The teams had to ensure not only that JWST captured the object, but that it did so without compromising the telescope's long-term mission or risking any critical subsystem. The success of this rapid response was a testament to years of preparation, cross-agency collaboration, and the ability to pivot quickly when the cosmos presents something truly unprecedented. In those tense minutes, the observatories on Earth and the telescope in space became a single, synchronized system, ready to capture data that would challenge every expectation of what an interstellar visitor could be. The chemical composition of 3I Atlas immediately stunned astronomers. Unlike typical comets, where water ice dominates activity and drives the formation of tails as the object approaches the Sun, this interstellar visitor was already highly active at 6 astronomical units, well beyond Jupiter's orbit, where sunlight is weak and most comets remain dormant. Instead of water, carbon dioxide was the primary volatile being released, venting at rates 8 times higher than water. This ratio of 8:1 is extraordinary, as even the most unusual solar system comets rarely exceed a ratio of 0.7. The tail of 3I Atlas reflected this unusual chemistry. With very little dust present, the tail appeared thin and ghostly, illuminated mainly by gas rather than solid particle. The carbon dioxide was not only abundant, but actively shaping the coma and tail in ways that defied expectation. Observations from multiple instruments, including JWST's NIR spec and other ground-based telescopes, confirmed that the activity was consistent and not an observational artifact. The gas sheets and faint brightening were persistent, indicating a steady outflow rather than a transient flare. This early activity so far from the Sun suggested that the comet's composition and thermal properties were fundamentally different from known comets. In a typical solar system comet, water ice begins to sublimate at closer distances, while CO2 and other volatiles contribute only later and to a lesser extent. In contrast, 3I Atlas seemed to have a main engine fueled by carbon dioxide, operating efficiently in the deep freeze of the outer solar system. The implications were profound. The composition hinted that 3I Atlas might have formed in an environment unlike anything in our solar system, possibly in a region where water was scarce and carbon dioxide ices dominated. Alternatively, it could indicate a process previously unknown to science, one capable of producing a volatile-rich body that activates so far from a star. The comet's early activity and extreme chemical ratios challenged existing models, forcing astronomers to reconsider assumptions about how interstellar objects form, evolve, and behave as they enter new star systems. As the data continued to stream in, it became clear that 3I Atlas was not just unusual, it was a chemical anomaly that could rewrite the rules for what comets can be, marking the beginning of an entirely new chapter in the study of interstellar visitors. Spectroscopic analysis of 3I Atlas revealed a chemical signature unlike anything seen before. The instruments detected strong and consistent nickel spectral lines spanning the ultraviolet and near-infrared bands, indicating a significant presence of metallic nickel in the comet's composition. At the same time, iron lines, which are normally found alongside nickel in both solar system comets and meteorites, were completely absent. The result was a nickel-to-iron ratio exceeding 40:1, a disparity so extreme that it defied all previous observations of celestial bodies. This anomaly was striking because, in typical comets and interstellar objects, nickel and iron appear together in roughly cosmic proportions. Even Borisov, the last well-studied interstellar visitor, adhered to these ratios, maintaining the expected balance between nickel and iron. With 3I Atlas, however, the absence of iron suggested either a formation process unlike anything known or conditions that selectively favored nickel over iron. Scientists considered every possibility, from instrumental errors to contamination, but repeated cross-checks with multiple telescopes and instruments confirmed that the signal was genuine. The presence of nickel in isolation hinted at extreme or exotic conditions in the comet's formation environment. Laboratory experiments suggest that volatile compounds like nickel carbonyl can form under certain conditions, but for iron to remain nearly absent, the parent body would likely need to have originated in a region where iron was trapped in minerals or otherwise unable to form volatile compounds. No known solar system comet shows this pattern, making 3I Atlas chemically unique and forcing astronomers to confront possibilities outside standard models of comet formation. This chemical anomaly also raised broader questions about the diversity of planetary systems. If an object could form with such a skewed composition, it implied that other star systems might produce worlds with chemistry radically different from our own. The data challenged assumptions about interstellar chemistry and hinted at processes in distant nebulae or planetary formation regions that humanity has never observed. The nickel dominance and iron absence did more than shock scientists. They suggested that 3I Atlas might carry information about a completely alien environment, offering a rare window into cosmic conditions that are otherwise inaccessible. Every measurement reinforced the idea that this comet was extraordinary, unlike anything seen before, and its chemical fingerprint was just the beginning of a puzzle that would unfold over the coming observation. Observations of 3I Atlas revealed that its motion was as unusual as its chemistry. Tracking networks, including pan-stars, recorded acceleration deviations that defied all expectations based on gravity and standard outgassing behavior. Over a span of just 72 hours, the comet's velocity increased by roughly 0.12 meters per second squared, an amount far greater than could be explained by solar heating or jets of gas alone. For an object approximately 11 kilometers across, this was comparable to witnessing a massive ship gain speed in the ocean without engines or wind. Even more perplexing were the tiny, abrupt jitters layered on top of the main acceleration. The comet's trajectory did not follow a smooth curve dictated by gravitational forces, but instead displayed subtle, sharp deviations as if something inside or attached to the object was intermittently pushing it forward. Analysts meticulously checked for software errors, instrument malfunctions, and observational biases, but all raw astrometry held firm. The acceleration was real, persistent, and completely anomalous. Photometric observations added another layer of mystery. Data from Gemini South and TESS revealed a periodic brightening every 7.2 hours, resembling a lighthouse beam sweeping across the sky. This rhythmic modulation was too regular to be explained by the slow tumble of a natural comet, and models attempting to account for it through irregular shape or rotation failed to reproduce the precision of the signal. Some researchers speculated about hollow or sheet-like structures reflecting sunlight, but each hypothesis presented its own problems. The combination of acceleration anomalies and precise light curves drew immediate comparisons to Oumuamua, another interstellar object whose trajectory and behavior defied conventional physics. However, 3I Atlas was larger, brighter, and exhibited a sharper, almost mechanical rhythm in its brightness changes. The more astronomers studied it, the more the object appeared to challenge both natural and previously understood cosmic processes. These dynamic irregularities elevated 3I Atlas from a chemical curiosity to a physical enigma. The data suggested that forces or mechanisms beyond standard cometary physics were at play, forcing scientists to consider exotic natural processes or, cautiously, the possibility of artificial or engineered structures. Every new observation intensified the debate, as the object's movement and light signature refused to conform to any familiar model. Photometric observations of 3I Atlas revealed a pattern that confounded astronomers. Data collected from Gemini South and TESS showed a precise, repeating brightening every 7.2 hours, a rhythm so regular it resembled the sweeping beam of a lighthouse. Unlike ordinary comets, which exhibit irregular rotations and unpredictable variations in brightness due to uneven surfaces and chaotic tumbling, 3I Atlas maintained an almost clockwork consistency in its light curve. Scientists attempted to model the phenomenon using natural explanations. They considered the possibility of a tumbling, irregularly shaped comet or a hollow, sheet-like structure reflecting sunlight at certain angles. Yet every model failed to reproduce the sharpness and regularity of the observed brightness changes. The period did not slow as the comet outgassed, contradicting expectations from rotational physics, and no combination of known shapes and reflective properties could account for the observed modulation. The precision of the light curve, combined with the unusual chemical composition and acceleration anomalies, pushed researchers to contemplate possibilities beyond conventional cometary physics. Some began to speculate about artificial or engineered structures, noting that a thin, reflective object could produce both the consistent periodic brightening and the anomalous accelerations observed. While no one claimed proof of design, the data forced scientists to confront scenarios that were once considered purely science. Fiction, the mechanical-like behavior heightened, the sense of mystery surrounding 3I Atlas. Every observation contradicted prior assumptions about how interstellar objects should behave, and the unusual combination of chemistry, motion, and brightness forced astronomers to consider that they were observing something entirely new. It was no longer merely a comet. It was a cosmic enigma challenging the boundaries between natural phenomena and possible engineered origins. The 7.2-hour light curve became a central focus of study, with astronomers worldwide analyzing the data, debating models, and checking for any possible observational error. Yet every cross-check confirmed the regularity. The object seemed to follow a rhythm unlike anything else in the solar system, or even among previously discovered interstellar visitors. This pattern, combined with all the other anomalies, marked 3I Atlas as one of the most extraordinary celestial objects ever observed. Throughout history, humans have encountered rare metals from the sky, long before advanced metallurgy existed. Archaeologists have discovered nickel-rich artifacts in ancient civilizations that far exceed what could have been produced by earthly smelting techniques. Tiny Egyptian beads, hammered and rolled into delicate shapes more than 5,000 years ago, contain nearly one-third nickel, a ratio that natural furnaces of the era could not achieve. Similarly, ceremonial daggers buried with pharaohs, such as those found with Tutankhamun, exhibit high nickel content along with traces of cobalt, consistent with meteorite composition rather than terrestrial iron. These artifacts reveal that cosmic material has been reaching Earth for millennia, sometimes incorporated into objects of cultural and ceremonial significance. The unique nickel-to-iron ratios in these items match patterns found in meteorites and echo the anomalies now seen in 3I Atlas. Scholars studying these relics note the crystalline structures, including the Widman-Stettin pattern, which form only in the slow cooling of metallic cores in space, confirming a non-terrestrial origin. The connection between these ancient skyfall metals and the composition of 3I Atlas is striking. Just as ancient humans recognized these metals as extraordinary, often imbuing them with mystical or religious significance, modern astronomers now encounter a celestial object that carries a similarly unusual chemical signature. The recurrence of nickel-rich material, both in historical artifacts and in this interstellar visitor, suggests a cosmic consistency, a material fingerprint delivered across space and time. This historical context provides not only a fascinating link between past and present, but also underscores the universality of nickel in certain celestial processes. It raises profound questions about how often such material reaches planetary systems, the environments that produce it, and the potential insights it holds into the formation of bodies beyond our solar system. In 3I Atlas, scientists are observing in real time the same kind of cosmic fingerprint that humans have been discovering on Earth for thousands of years, bridging ancient wonder with cutting-edge astrophysical discovery. The unprecedented combination of chemical, dynamic, and photometric anomalies in 3I Atlas has ignited intense debate within the scientific community. On one side, some researchers argue for rare but natural explanations, suggesting that the comet's unusual nickel-to-iron ratio, extreme carbon dioxide dominance, and early activation could result from formation in a carbon-rich nebula or a parent body with conditions unlike anything in our solar system. These proponents emphasize that while extraordinary, the comet might still fit within the bounds of natural astrophysical processes that have yet to be fully understood. On the other side, some scientists cautiously raise the possibility of artificial or engineered origins. The sharp 7.2-hour light curve, mechanical-like acceleration, and precise, repetitive patterns are difficult to reconcile with known natural behaviors of interstellar objects. These features, combined with the extreme chemical composition, evoke comparisons to Oumuamua, the first well-studied interstellar visitor, which also exhibited acceleration without obvious cometary outgassing. Such recurring anomalies suggest that these objects might not all conform to conventional models, prompting questions that skirt the boundary between astrophysics and speculative engineering hypotheses. The debate has spilled into peer-reviewed preprints, open-access archives, and social media forums, with astronomers worldwide scrutinizing every piece of data. Each new observation, whether spectral line, photometric curve, or acceleration measurement, forces a reassessment of the models, and no consensus has yet emerged. Some caution against jumping to conclusions, recalling the prolonged debates over Oumuamua, which, despite years of analysis, left critical questions unresolved. Others argue that ignoring the possibility of artificial origins limits the scope of inquiry in a situation where the natural explanations are already stretched to extremes. Amid the controversy, NASA's Planetary Defense Office quietly categorized 3I Atlas as a high anomaly object. While not a threat to Earth, its unpredictable behavior and unique properties place it in a special category reserved for objects that challenge conventional understanding. Internal discussions track it meticulously, noting that extraordinary claims require extraordinary evidence. But even the most skeptical voices admit that this interstellar visitor is rewriting the known rules for cometary and interstellar phenomena. Ultimately, 3I Atlas has become a focal point for examining the boundaries of natural cosmic processes. Its unusual properties force scientists to confront questions about the diversity of planetary systems, the potential for unknown physical mechanisms, and the rare possibility of engineered artifacts in space. The debate is ongoing, reflecting both the excitement and the uncertainty inherent in encountering something completely unlike anything humanity has observed before. NASA has officially classified 3I Atlas as a high anomaly object, acknowledging that it defies conventional categorization. Despite intensive observation campaigns, its extraordinary chemical composition, with carbon dioxide vastly outpacing water and nickel dominating while iron is nearly absent, remains unexplained by current cometary models. The comet's dynamic behavior, including erratic acceleration and subtle trajectory jitters, adds further complexity, indicating forces or mechanisms beyond standard gravitational and outgassing processes. Photometric data only deepens the mystery. The precise 7.2-hour periodic brightening behaves unlike any known comet, suggesting an almost mechanical regularity in its rotation or structure. Attempts to model the light curve through natural shapes, tumbling, or reflective surfaces have failed to fully explain the observed consistency, leaving open the possibility of either an unknown natural process or, cautiously, engineered features. The combination of chemical, physical, and photometric anomalies makes 3I Atlas one of the most perplexing interstellar visitors ever recorded. While scientists continue to gather data and cross-check observations from JWST, ground-based telescopes, and other instruments, no definitive explanation has emerged. Peer-reviewed studies, preprints, and open-access archives reflect ongoing debates, with some emphasizing exotic natural formation scenarios and others noting the uncanny. Parallels to prior interstellar anomalies like Oumuamua. The official designation as a high anomaly object underscores the uncertainty surrounding 3I Atlas. It is not considered a threat, but it represents a scientific wildcard, forcing experts to reconsider fundamental assumptions about the diversity of interstellar bodies, planetary system formation, and the possible limits of natural processes. Until further observations are made, the true nature of 3I Atlas, whether it is a cosmic fluke, Kotofidenthauerns Naasi Chand, a messenger from an alien chemical environment, or something deliberately engineered, remains an open question, preserving both the wonder and the caution that come with exploring the unknown reaches of the universe. The story of 3I Atlas is far from over. Each new observation peels back another layer of mystery, revealing a cosmic visitor that challenges everything we thought we knew about interstellar objects. Its unusual chemistry, erratic motion, and mechanical-like light curve hint at forces and processes beyond our current understanding, keeping scientists, historians, and enthusiasts alike on the edge of discovery. As telescopes continue to track its journey through the solar system, every spectral line and every flicker of light becomes a clue to its origin. Whether a product of exotic natural processes, a messenger from a distant star system, or something more deliberate, 3I Atlas reminds us that the universe is far stranger and far more wondrous than we can imagine. For now, we watch, we measure, and we wonder, knowing that each revelation brings us closer to understanding not just this singular visitor, but the vast, untamed possibilities that lie beyond our solar neighborhood. The cosmos has thrown down a challenge, and humanity is only beginning to answer. What if everything you've been told about the moon is a lie? When renowned physicist Michio Kaku broke down in tears during his presentation at a major space science symposium in Geneva, the room fell silent. the man who has spent decades explaining the mysteries of the universe to millions, was visibly shaken by what he was about to reveal. The data he presented that day didn't just challenge our understanding of the moon, it shattered it completely. Quantum deep imaging satellites, subsurface radar, and gravitational lensing technology had uncovered something so shocking that multiple international agencies verified the findings before Kaku was authorized to speak. What they found beneath the lunar surface defies everything we thought we knew about natural celestial formation. It began in Geneva, at one of the most anticipated gatherings of scientists, astronomers, and futurists from around the globe. The symposium was known for unveiling bold theories and new discoveries, but this year, anticipation carried an unusual weight. When Michio Kaku, the world-renowned theoretical physicist and futurist, walked onto the stage, the room fell into a silence that was more than just respect. It was curiosity mixed with unease. Kaku had built his reputation on being a bridge between hard science and visionary speculation. He could talk about string theory one moment and humanity's future among the stars the next. Audiences expected imagination from him, but they also expected clarity and evidence. Yet that morning in Geneva, his demeanor was different. There was no playful humor in his eyes, no casual warmth in his gestures. Instead, he carried himself with a kind of solemn urgency, as if the information he was about to reveal weighed heavily on his shoulders. The title of his presentation, displayed across a vast screen, read, "The Moon, a Paradigm Shift in Understanding." The words alone stirred murmurs among the crowd. Most had expected the talk to cover well-worn territory, perhaps updates on lunar colonization plans, NASA's Artemis program, or speculative ideas about mining lunar resources. Some even assumed it might be a futuristic pitch about using the moon as a launching base for Mars missions. But Kaku's voice, steady yet unusually subdued, quickly shattered those expectations. He began by reminding the audience of the moon's place in human imagination, how every civilization had looked up at it with reverence, woven it into myths, and used it to mark time. But then he paused, and with a quiet intensity said, "What we thought we knew about the moon is about to change." The room shifted. Scientists who had come prepared to take notes on orbital mechanics or colonization strategies now leaned forward with furrowed brows. This was not going to be another technical update. This was going to challenge the very foundation of how humanity understood its closest celestial neighbor. Kaku explained that the findings he was about to share were not his alone. They were the product of an unprecedented collaboration between space agencies in Europe, Asia, and beyond. These agencies had recently deployed a new generation of satellites equipped with quantum deep imaging systems, gravitational lensing, arrays, and radar capable of penetrating beneath the lunar surface with greater precision than ever before. The data, he said, did not just fill in gaps in our understanding, it tore open the framework entirely. As he spoke, images began to appear. Behind him, high-resolution scans of the moon, patterns and colors highlighting areas that most of the world had never seen. He let the images linger in silence, as though giving the audience time to prepare themselves. Then, with deliberate pacing, he delivered the statement that would ripple far beyond that auditorium. "The moon may not be what we think it is." Gasps and whispers spread through the hall. This was no longer just a presentation, it was a revelation. Kaku, usually so animated in his delivery, stood motionless, his voice steady, his eyes fixed on the audience as though measuring their reactions. It was the beginning of a story that would leave the scientific world and the public at large forever changed. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. After his startling introduction, Michio Kaku shifted the audience's attention to the cutting-edge technology that had made these revelations possible. He explained that for decades, the moon had been studied with telescopes, orbiters, and seismic data from the Apollo missions, but all of those tools had provided only a partial picture. The moon, for all its familiarity, remained a mystery. That mystery began to unravel with the deployment of a new generation of instruments, machines so precise that they seemed almost futuristic in their capabilities. These were not the old radar sweeps or grainy photographs. These were quantum deep imaging satellites, able to bend the very fabric of space-time through gravitational lensing to reveal what lay hidden beneath the surface. They were paired with subsurface radar systems capable of probing hundreds of kilometers deep into the lunar crust, mapping structures that had never been seen before. The project was unprecedented in scope. Agencies from Europe, Asia, and smaller spacefaring nations pooled resources, sharing data rather than competing. For the first time, humanity had eyes that could see the moon not as a flat, cratered sphere of dust and rock, but as a layered object with secrets buried far beneath its surface. Kaku described the findings slowly, letting the weight of each word settle over the audience. At first, the data seemed routine: density maps, heat signatures, gravitational fluctuations. But, as the analysis progressed, the results defied every conventional model of lunar formation. The moon's internal density readings were inconsistent, not the gradual, natural layering one would expect from a body formed in a cosmic collision, but sharp disparities, voids where solid rock should have been. Some cavities stretched for hundreds of kilometers, too vast to be dismissed as volcanic tubes or natural hollows. Even more unsettling was their arrangement: symmetrical, repeating, evenly spaced, as though laid out according to a plan. The images on the screen behind Kaku began to change. Grainy radar scans gave way to clean, geometric outlines glowing against the blackness of space. Structures, grids, and what looked like corridors of emptiness threaded through the moon's interior. The auditorium grew tense. Scientists who had dismissed such ideas as fringe speculation now sat frozen, confronted with evidence that could not be ignored. Kaku added another layer. The scans had revealed reflective materials buried deep under the lunar regolith, alloys that gleamed unnaturally in thermal and radar imagery. These were not random deposits of ore. They reflected energy in ways that hinted at engineered surfaces, like panels or casings, preserved under billions of years of dust and impact. He explained that these anomalies weren't isolated. Taken together, the cavities, the geometry, the reflective layers, and the density irregularities painted a picture that no current model of lunar evolution could account for. "This is not the moon we thought we knew," he said gravely. The room was silent, save for the occasional rustle of paper or hurried scribbling of notes. The air seemed charged, as though every person present understood they were witnessing a moment in history. Humanity had stared at the moon for millennia, written poems to it, worshipped it, and studied it. But for the first time, science was beginning to peel back its skin, and what it revealed was something utterly unexpected. As the audience sat in silence, Kaku advanced to the next sequence of findings. This was where the data stopped being unusual and began becoming impossible to dismiss. On the giant screen behind him, scans of the moon's interior revealed a startling truth. The satellite that humanity had always considered a natural companion was not behaving like one at all. The first anomaly was sheer scale. Within the moon's body, researchers had discovered vast internal cavities, hollows stretching hundreds of kilometers in length. Natural explanations such as lava tubes or collapsed voids had been considered, but these cavities were different. They were too vast, too consistent, and they appeared not as chaotic tunnels, but as ordered chambers spread in regular patterns across multiple regions. It was as if someone had hollowed out enormous portions of the moon with deliberate precision. Kaku paused on one image that drew collective gasps. It showed cavities aligned in a near-perfect grid, each separated by similar distances, forming something more like an architectural blueprint than a geological accident. This was not randomness. This was geometry on a planetary scale. The second anomaly deepened the unease. Within these cavities, radar and thermal imaging detected faint reflections that did not belong. Scientists had long understood the lunar regolith, dust and rock billions of years old, was a chaotic mixture of debris from countless impacts. But these reflections suggested the presence of metallic alloys buried far beneath the surface. Alloys arranged not in veins or scattered patches, but in flat, uniform planes. Kaku explained that these reflective signatures resembled the smooth surfaces of engineered structures, plates, casings, or perhaps shells, designed to endure eons of bombardment. Their consistency across multiple regions hinted at a system, a pattern of design. They were not random minerals born of cosmic chance, but evidence of construction. The third anomaly tied everything together. As researchers mapped the cavities and alloys, they noticed that many of the geometric formations intersected cleanly, like beams meeting at right angles or panels overlapping along straight lines. These were shapes foreign to natural geology, but deeply familiar to human eyes. The shapes of design, the signatures of architecture. Behind Kaku, the screen lit up with enhanced images, glowing outlines of honeycomb-like grids, faint but unmistakable. The crowd's silence deepened into something heavier, more electric. The evidence was no longer just statistical irregularities or unexplained signals. It was visual, undeniable. This, Kaku said, pointing to the glowing grid, is not what we expect from nature. These are the hallmarks of design. His beauty voice carried a gravity that matched the revelation itself. He did not rush, did not embellish. He simply presented the data and let the images speak for themselves. Some scientists shifted uncomfortably in their seats. Others scribbled furiously in their notebooks. A few simply stared at the screen, wide-eyed, unable to look away. The seeker realization was setting in. If these anomalies were real, then the moon was not simply a rock captured by Earth. 6 minutes. That's all the time astronomers had to coordinate a global emergency response when Atlas appeared in our telescopes, behaving like nothing we'd ever seen before. Picture this: ground control rooms erupting into organized chaos, ESA servers calculating trajectories at breakneck speed, and the most expensive space telescope ever built pivoting away from years of scheduled observations to focus on a single, terrifying anomaly. What they discovered in those crucial innovation has left the scientific community scrambling for explanation, and what we're about to show you exactly why this discovery is being called worse than anyone expected. On August 6, 2025, the James Webb Space Telescope entered a rare and critical emergency override to capture data on 3I Atlas, an interstellar object unlike anything astronomers had observed before. Normally, JWST operates on a strict schedule, with every observation carefully planned weeks or even months in advance, balancing the delicate choreography of orbital mechanics, fuel consumption, and instrument availability. Pausing this finely tuned program is not done lightly, as even a small miscalculation can cost days or weeks of science, or risk damaging sensitive subsystems. The urgency arose from ground-based observations showing that 3I Atlas was accelerating and displaying unexpected spectral signatures. Within minutes, the mission operations team had to decide whether to override the main science program. Approval for such an override required unanimous agreement from the highest levels of the project, including the project scientist, because the risks were high and the opportunity fleeting. The telescope pivoted, instruments activated, and the entire operations center was on high alert, monitoring every telemetry signal as the team raced to ensure nothing went wrong.